Okay, hello guys. We are doing our class, our YouTube video notes here on the subject of stoichiometry, chapter 12 in our book. And what it means in technical definition is it's the calculation of quantities, the amount of reactants and products in a chemical reaction. What we discussed is, what does stoichiometry really mean? It means that we're going to read chemical equations, things that describe chemical reactions. We're going to read them as recipes. Well, we know how much goes in and how much comes out. The two things that we're going to need, some basic skills, is we're going to have to use our periodic table which of course is this, and you've got several of them. There's one in the back of the book. For calculating molar masses, which we've done a lot of, and we're also going to need to use some basic dimensional analysis skills. And of course, we also need to do some of our newer stuff, which is interpret chemical equations or balanced chemical equations adequately. So the first thing we're going to want to do with stoichiometry is, first of all, make sure that we're actually looking at a balanced chemical equation. If it's not balanced, everything that you're going to do is just going to be an exercise in frustration. It does have to be balanced. This equation that we have in front of you, 2 potassiums, excuse me, guys, 2 potassiums right here plus 2 waters yields 2 potassium hydroxides and 1 H2 gas molecule. So let's talk a little bit about what's involved and how do we interpret that. And one of the ones that we started out with is looking at it by an atom basis. So we could read this as, like we said, 2 potassium atoms, 2 water molecules will yield 2 compounds of potassium hydroxide and 1 H2 molecule. Imagine if we think about it as a recipe, though, and we want to scale this thing up. We want to double the amount of cookies that we're going to make. We have to double the ingredients. So we could also think about changing the ingredients, but they all have to change by the same amounts, and that means that the products will change by the same amounts. So if I want to double the amount of potassium hydroxide that I'm expecting and go from 2 to 4 atoms, well, that means what do I have to put into the recipe? I need to put in 4 potassiums and 4 H2Os, and I expect to get 4 potassium hydroxides and 1 H2. The point is, these coefficients are ratios that we're going to look at later. They have to stay fixed to one another. We go all the way up to 1,000,000. We could multiply it by 1,000,000 times, and those ratios would have to be the same. And in fact, that's what chemists do in practice, is look at them not atom by atom, but mole by mole. So the best way for us to start reading equations like this is not atom by atom or molecule by molecule, but mole by mole. So we want to read it this way. 2 moles of potassium react with 2 moles of water and will yield 2 moles of potassium hydroxide and 1 mole of hydrogen gas. All right, so let's go ahead and get started. I think the best way to learn stoichiometry is actually through a few examples rather than definitions and procedures. So we're going to look at the same equation. We have the periodic table in front of us, and we're going to use one of those basic skills. First off, we're going to find the molar mass of the elements or the compounds involved in this equation. And remember, the molar mass is really simple if we have the periodic table in front of us, and I actually have them already in blue. So on this slide, the molar masses are in blue here. So these are the molar masses right here. So let's take a look at potassium has a molar mass. If I look at the periodic table, I'm going to round to the ones place, of 39 grams. So if I have 39 grams of potassium, I've got a mole of it. Water was 18, remember. So if I have 18 grams of water, I have a mole, or Avogadro's number, of water molecules. Potassium hydroxide, a little bit of work with the periodic table would show us that 56 would do it, right? 39 plus 16 plus 1 would give me 56, and then H2, 2 grams of H2 per mole of H2. So that's what we have then in blue, is the moles, or the molar mass of our compounds involved. So what I want to do next is just a quick exercise to show you that if we do have a balanced chemical equation and we have our molar masses right, the law of conservation of mass should show up. So let's go ahead and do this. Here is 39 grams per mole for our potassium, and we're dealing with 2 moles of it. So I'm going to multiply on this side 2 moles of potassium. And what are we going to find? We're going to find out that mole of potassium cancels mole of potassium, and what went in as a reactant was 78 grams of potassium. I'm going to do the other ones really quick as well. Here's water. There's 2 moles of H2O. So mole of H2O cancels mole of H2O. So we find out that in our ingredients we have 36 grams of H2O in there. Go over to the product side. Again, 2 moles of potassium, so I multiply 2 moles of potassium hydroxide rather, so potassium hydroxide moles cancels potassium hydroxide moles, and I have 112 grams of potassium hydroxide as a product. And then finally, right, no coefficient means 1, so 1 mole of H2 times 2 grams of H2 per mole of H2. The moles of H2 will cancel out, and I will be left with 2 grams of H2. So real quickly, when we add these up, there's 114 grams of product. And what do we start with? Well, if we add those up, lo and behold, you're going to find that that was 114 grams of reactant. So it does show us the conservation of mass. It also shows you how important it is to start with a balanced equation. You can bet that if it wasn't balanced, mass would not be conserved, and I know then there's an issue with my stoichiometry in that case. All right, so what we just looked at was the molar masses. We have done those before. You need a periodic table. The other piece of information that we need, the other relationships that we need to solve a stoichiometry problem is going to be what's called a molar ratio. So a molar ratio is real easy to get if you have a balanced chemical reaction in front of you. You just have to read the chemical reaction. So I have these things, all of the molar ratios for this reaction stated. You don't always need to write all of them. I just want to show you that you can do them, and they're really easy to get. All we're saying is, hey, for this one, look at this. 2 moles of potassium is related to 2 moles of water. 2 moles of potassium is related to 2 moles of potassium hydroxide, and 2 moles of potassium is related to 1 mole of H2. So that's all these ratios do, is relate those to one another. And remember, the inverse of these is also true. It's just as true to say 1 mole of H2 is related to 2 moles of potassium. So I've shown you the rest of them on the bottom here. Here's the relationship between water and potassium hydroxide. Here's the relationship then between water and hydrogen. And then the final one would be potassium hydroxide and hydrogen. 2 moles of potassium hydroxide related to 1 mole of hydrogen. So these two relationships, these two ratios, the molar mass from the preceding page and the molar ratio, is all we really need to solve almost any stoichiometry problem. So let's see how that might happen with a couple examples here. Okay, a real easy stoichiometry problem. In this one, how many moles of hydrogen gas will be produced with 5 moles of potassium in excess water? Excess water here, that just means that we don't have to worry about running out of water in this reaction. We have plenty of it to make it happen. So 5 moles of potassium will yield how much hydrogen? Well, the relationship that we just went over is a molar relationship, a molar ratio. There is 1 mole of hydrogen gas produced for every 2 moles of potassium used as reactants. Now, I always suggest when you start dimensional analysis problems that you start with what a known quantity and what you want up top. I want my answer to be in how many moles of hydrogen gas. So I'm going to start with this molar ratio. 1 mole of H2 per 2 moles of potassium. Real simple. And then how many moles of potassium am I dealing with? I'm dealing with 5 moles of potassium. So this is actually it, guys. It's already solved. Moles of potassium cancels moles of potassium. So I carry out the arithmetic here. 1 times 5 divided by 2 is 2.5, but just as importantly, what unit didn't cancel? Moles of H2. Should make sense, right? We expect half the number of moles of hydrogen as potassium. So if we started with 5, we expect half of that, 2.5. Okay, slightly harder problem because it requires one more step in the dimensional analysis. How many grams of potassium hydroxide will be produced from 3.5 moles of water and excess potassium. So in this case, we've got plenty of potassium, but we only have 3.5 moles of water to work with. So again, we want our answers to be in how many grams of potassium hydroxide. So I start with something that I know about grams of potassium hydroxide. Here is the molar mass of potassium hydroxide. So that's a good place for me to start. 56 grams of KOH, and the relation is that's related to 1 mole of KOH. Second relationship is going to be a molar relationship then. I know how many moles of water I'm dealing with, so I have to think about that. I'm going to use this relationship that I found out from every 2 moles of water produces 2 moles of potassium hydroxide. So 2 moles of KOH per 2 moles of H2O. And we're almost done here. How many moles of water are we talking about? 3.5 moles of H2O. So the chemistry is the dimensional analysis, right? Moles of H2O cancels moles of H2O, mole of KOH cancels mole of KOH, and I'm left with grams of KOH. So the answer should be, I think, if we do carry out the arithmetic, it should be 196, and then super important, never just numbers in science, grams of potassium hydroxide. Okay, so here's our mastery problem. How many grams of carbon dioxide are produced in the combustion of 10 moles of octane with excess oxygen? This is mastery for a couple reasons. A, I haven't given you the skeleton equation or balanced equation. You need to figure it out knowing that it's combustion. So the solution would start this way. So all combustion reactions have sort of the same looking skeleton equation. We've got a hydrocarbon here. One of the reactants has to be oxygen gas, and the byproducts, or the products rather, we're going to be CO2, carbon dioxide, and water. So this is a skeleton. It needs to be balanced in order to do stoichiometry. So the balancing, with a little thought, would be this: 2, 25, 16, and 18. So the coefficients aren't quite as easy. Okay, so quickly, what do we want? We want how many grams of carbon dioxide are produced by the combustion of 10 moles of octane. We've got the balanced equation there. So the first thing I'm going to do is I'm going to start with a known relationship with grams of carbon dioxide. So I know, using the periodic table, that there are 44 grams of CO2 per 1 mole of CO2. From the balanced equation, I know the stoichiometric coefficients. 16 grams of CO2 for every 2 moles, or 16 moles of CO2 rather, I'm sorry, for every 2 moles of octane. So I could do this: 16 moles of CO2 per 2 moles of octane. And now I have moles of CO2 canceling, and I want to cancel moles of octane. At this point, it's pretty simple. I've got 10 moles of octane that I'm dealing with. So moles of octane cancels, and my answer will be in grams of CO2. And if you carry out the arithmetic, you should get 3,520. A little over 3.5 kilograms of CO2. So that would be an example of how do we estimate, greenhouse gas emissions. If we know how much gasoline we're burning, we do know how much CO2 should come out as a byproduct of that reaction.